Now, any questions before we start? Okay, so now we will be starting translations. So we will be basically dealing with objects that are both rotating around some axis, plus it is being translated. Now again, we will start with the simple cases. We will first study only a system in which the axis of rotation, let's say, it's not accelerating. So we have this wheel, let's say, it's just rolling with constant velocity. The center of mass is moving with constant velocity. Now this is kind of probably the easiest possible case that you can think of, because if you go to another reference frame which moves with the axis, in that reference frame, which is still an inertial reference frame, it is just, the wheel will be just rotating and nothing else. In your reference frame, it is rotating and also at the same time moving with constant velocity. In my reference frame, it's just rotating around a fixed axis. And we already know how to deal with rotations around a fixed axis. So let's say axis of rotation moving with constant velocity. Now this axis of rotation need not pass through the center of mass. It can be an arbitrary axis, but the critical thing, at least for this initial discussion, will be the axis of rotation is just moving with constant velocity. Now in this case, we can go to another reference frame which moves with the axis of rotation, and in that reference frame, the axis of rotation is just fixed. In my reference frame, it is fixed. In your reference frame, it is moving with constant velocity. And we know how to go from one reference frame to the other reference frame in terms of velocity. Let's just review them again. Change of reference frames. Now this is the reference frame that is moving with the axis of rotation, and this is your reference frame. So O prime moves with the axis of rotation. So in the O prime reference frame, all these points, now the center axis of rotation doesn't move. In my reference frame, it is constant. In your reference frame, it will have a velocity, and let's call that velocity v. So let's say let's call this r vector, dr by dt. Let's call it capital V. This is the velocity of the axis of rotation. We can just imagine any point as I'm moving in your reference frame. We can just consider any point over here. Let's say this point over here in the O prime reference frame, it will have a position, let's say r prime, and its position relative to your reference frame will be just r. And we also know that r is nothing but r prime plus v large R. So v is the velocity that you observe of a point, and v prime is the velocity that I observe plus capital V, which is the velocity of the center of mass. So this is how we would calculate the velocity of a point on our rigid body. This is the velocity of the object, of the point on the rigid body relative to the axis of rotation. This is the velocity of the axis of rotation. This is the velocity relative to the observer. Now, one important such motion will be rolling without slipping. Now, what we mean by rolling without slipping is this motion. Or let's take the ball. This is rolling without slipping. Now, the other example is when I was rotating it. Initially, if I rotate it and let it go, of course, it now bounced. It shouldn't bounce, but initially, there was some slipping motion. Because initially, the bottom had some velocity, the ground didn't have any velocity, so there was this slipping motion. At the same time, there was the friction force, and which created it to accelerate in the forward direction. After some time, then it just starts rolling without slipping. It will start moving at constant velocity. This is the kind of motion that we will be studying. Now, in this rolling without slipping, this is the wheel, this is the ground. The angular velocity is initially in this sense. So is it rotating clockwise or counterclockwise? It is rotating counterclockwise. Now, let's first go to the reference frame in which the axis is fixed. Now, what is the velocity of the bottom point in the reference frame that the axis is fixed? So if you are in that reference frame, so if omega is pointing towards you, it means it's rotating like this. Okay, what is the direction of the velocity of the bottom point? It's in this sense. Let's call it VB. What is the velocity of the top point? This top point? It's in that sense. Okay, the velocity of this point? Downward. It's the, okay. This is relative to the reference frame which is at rest. Now, what can you say about their magnitudes? Remember, it's a wheel. So all these points are from at the same distance. So VL, the magnitude is equal to VR, the magnitude V top, V bottom. And they are all equal to, in terms of angular velocity and the radius, omega times r. Now let's go to our reference frame, which is moving with the wheel. So initially we just looked at the reference frame in which the coordinate axis was fixed, but we are actually interested in the other reference frame, in this one. What is the relative velocity of the point touching the ground and that point? Is the bottom point slipping or trying to slip? So let me ask you this question before. What is the total force acting on the system? It is, remember, the axis or if this is the wheel, the axis or the center of mass is moving with constant velocity. What is the total force? What are the horizontal forces acting on it? Are there any? There is no horizontal force. There is no if it is moving with constant velocity, if we can ignore drag forces, there is no horizontal force. There is no friction force, no force whatsoever. If it is moving at constant velocity. So there is no acceleration. Okay, so if there is no friction force, you see, the coefficient of friction is non-zero. Nevertheless, there is no friction force, which just means that the surfaces touching each other, they are not trying to slip over each other. If they are not trying to slip over each other, they are definitely not slipping relative to each other, which means their velocities are the same. Ground is at rest, so the point that is touching the ground should be at rest. So in your reference frame, this top point, VB, is equal to 0. It has 0 velocity. Now that tells me already one thing. Remember this translation law. VB, this is the velocity in your reference frame, in the reference frame in which the axis is translating. This should be equal to VB. This is the velocity of the bottom point in the reference frame that is moving with the axis, plus large V. Large V is the velocity of the axis relative to your reference frame. This is 0. Which basically means that VB in orange, let's just call it VB prime. This is equal to minus V, or V is equal to minus VB prime. So let's go back. Remember, VB, it's initially in that, VB prime is in that direction. Velocity of the axis, that's large V, is in the opposite direction. So this is moving with velocity V in that direction. Do you agree? And the magnitude of this large V is equal to the magnitude of VB prime, which is nothing but omega r. Do you all agree? Now let's look at the velocity of the top point. You see, basically what we do to go to your reference frame is VB should be equal to V is equal to V prime plus minus VB prime, or V is equal to V prime plus V. This is what we always do. We will just add capital V, that is the velocity of the axis, to the velocities in the rest frame of the axis to obtain the velocities in your reference frame. So what will be the velocity of the top point in your reference frame? You see, in the reference frame in which the axis is fixed, this is moving with velocity V in that direction, with speed V in that direction. Agree? Now the axis now also moves with speed V in that direction. The top point is moving with speed V in the same direction relative to the axis. So the top point, what's the speed of the top point? in your reference frame, it's just 2v. It's 2v. Let me just draw it again. This is v. This point is now 2v. The magnitude of 2v is omega times 2r. Magnitude of v is omega times r. Well, let's look at this point. Okay, this is rotating like this, and at the same time it is moving. The center of the axis of rotation is moving with velocity v in that direction. This point over here is moving downward with velocity v relative to the axis. So relative to you, what is the speed of that point? This point? V in that direction, v in the downward direction. So the total velocity of that point is in that direction. So at this point, we'll be moving in this direction. Let's call it v prime. V prime is omega r square root of 2. Well, let us note one more thing. This is r, so this is r square root of 2. Well, we can repeat the same exercise for this point, for the other point, and it will be moving in this direction with velocity v double prime, and v double prime is equal to omega r square root of 2. So this length is also r square root of 2. And these are also perpendicular to each other. Okay, does it start to ring any bells? Does it look like anything? So we have this rigid body. The velocities at any point, well, here we just took three representative points, but if you repeat the exercise for an arbitrary point over here, let's say, you will see that the velocity of that point will be perpendicular to the line connecting that point to the bottom. The velocity over here will be perpendicular to this line. Let's say it's v triple prime, and the magnitude of v triple prime, is perpendicular, is omega times, let's just call that distance d, omega times d. Whichever point you take, the velocity of that point is always perpendicular to this line. Furthermore, its speed is the angular velocity multiplied by the distance from this line. Does it resemble any motion, any kind of motion? It's just rotation. Instantaneously, this whole thing is rotating around this point. This point is at rest. That axis is called this is instantaneous axis of, okay, there is some more, too much. Axis of rotation. So at that point over here, our object is, at that instant, it is rotating around that point. The angular velocity, by the way, is the same. The angular velocity of the object around the axis of rotation, around this axis, was omega. Now it's rotating around this axis with the same angular velocity, not a different one. And Well, it's just at this instant, this axis is fixed. It is rotating around that point. Now, is this point clear? So if you have rolling without slipping, now first of all, this is our criteria. V should be equal to omega r. V is the speed of the axis. If you have a wheel that is rolling, or any spherical object that is rolling without slipping, in that case, the speed of this axis, the center, should be equal to its angular velocity times its radius. Otherwise, it will be slipping. If it is moving, let's say if it is rotating, if it is moving too slowly, of course it will slip. If it is moving too fast, then it will slip. Only if this condition is satisfied, it will just roll without slipping. Now let's go back to this example, this case. So now we have two axes. Okay, first of all, why is the angular velocity the same? If you look at this picture, this example, we have two different representations of the same thing. We said that, okay, there is the central axis, which is moving at constant velocity, and it is rotating with zero angular acceleration. That is one picture of this process, this example. Now we discovered another description of the same thing. As it is rolling without slipping, at every instant we can say that it is rotating around the point of contact. That point of contact is not moving. And it's not moving. It is at that instant it is rotating around that axis with the same angular velocity. So we have these two different descriptions. We can describe it as a rotation around this axis, where that axis is moving, or we can describe it as if it is rotating around this axis and the axis is fixed. In fact, the problem is, in a sense, even worse. Any axis would do. For example, I can treat this system, you see, this is the wheel, this is what you observe. I can say that once we add the translational motion, I can say that at this instant, the wheel, okay, you will probably choose this axis as this axis of rotation and it is fixed, but I can claim that it is rotating around this point, but that point is making uniform circular motion. It is up to you, it is your choice, you can just choose any one of them. All of them will be true. Is this point clear? Now the axis of rotation, once you allow the axis to make translational motion, it's just free, it's arbitrary. It doesn't have to be what is obvious. So in this example, the obvious choice of the axis of rotation is this one. That will be the obvious choice. It will be the simplest choice also, because it's an axis that is fixed. And we know how to deal with it. I can also choose this axis. I can say that the wheel is rotating around that axis, and at the same time that axis is doing some circular motion. This is also a valid description of the same phenomenon. Now, if you try it, now as it's rotating, I can feel that these strings are rotating around my finger. So the wheel is rotating around my finger as it's moved. It's rotating around my finger. And furthermore, once it completes one full rotation around this axis, it also completes one full rotation around my finger, where everything is back to its initial orientation. So that is why the angular velocity is always the same, no matter which reference frame you choose. It's just like which axis you choose. It's just like the reference frames. You see, as long as you are using inertial reference frames, acceleration is always the same. Velocities might differ, but acceleration is always the same. Just like that, whichever axis of rotation you choose to describe your motion, The angular velocity of an object is independent of your choice of the axis. Whichever axis you choose, the angular velocity is always the same. So this is one example where we explicitly showed it. The angular velocity, whether we treat it as if it's rotating around this point or it's rotating around this point, it's always the same angular velocity. In a sense, you can say that angular velocity is not a property of the reference frame. It's a property of the object as a whole. If you choose your rotation axis, if you choose a different axis to describe your rotational motion, angular velocity will still be the same. And hence the angular acceleration will also be the same. So angular acceleration, since it depends on angular velocity, it is also independent of which axis you choose. Of course, some of these reference frames, if you prefer to go to a reference frame in which your axis of rotation is at rest, that reference frame need not be an inertial reference frame. So you might not be able to apply Newton's law or the other properties like the torque and the relation between the torque and the angular acceleration. You might not be able to apply those things. But there will be one special axis, in which case, even if that axis is moving, if we move with that axis, it will be a non-inertial reference frame. Nevertheless, all the properties will still hold. And it's an axis that goes through the center of mass. So as long as you describe your object as the translational motion of the center of mass plus any rotations around the center of mass, whatever we derived about the rotations, about the torques, it will be still valid as long as you calculate the torque and the angular velocity relative to the center of mass. And the acceleration of the center of mass you can just describe in an inertial reference frame. Now that we will do in more detail on Thursday. But before you go, let's do a short example here. So let's assume we have a circular object, a wheel. It is just rolling down an inclined plane. What will be its acceleration? Let's say its mass is m, its radius is r, its moment of inertia is I. Now we had already seen that if you just look at it at an arbitrary instant, at this instant, this point is at rest. So at that point, it will be doing rolling without slipping. This is important. It's rolling without slipping. If it starts slipping, everything will change, and we will study it later on. But let's first, this simple example, rolling without slipping. We had already seen that this point is at rest, and we can just treat the motion as if it is rotating around this point. Now, if it is rotating around this point, we can calculate its angular acceleration. We had already done one example of this one, but we still need to calculate the torque if we want to calculate the angular acceleration around that point. Now, if we just enlarge that piece a bit, you see, this is our ring. So this is the inclined plane. What are the forces acting on this one? On my object, on my mass? There is the weight. What else? What other forces are there? There is the normal force. What else? There is the friction force. What is the direction of the friction force, if there is any? Upwards or downwards? We don't know. I mean, we don't know. It will be upward, but we will drive it. I mean, you see, for example, in the case of this one, if there was no incline, if it is just rolling at constant velocity, there is no friction force. If it was slipping, you see, if it was rotating in this sense, and if I just let it go on the ground, then the friction force would be in that direction. If it was going in the other way, if I just throw it like this, the friction force would have been in this direction. So I don't really know which direction the friction force will be. But I assume that it will be in the backward direction. In the worst case, if we calculate the friction force, it will have a negative component in that direction. We don't know. I mean, that's why I'm saying that I don't know. Maybe it's in the opposite direction. We will find out what friction force is. What is the torque relative to this point? Let's say this is the z-axis. Which forces create torque? Does the normal force create a torque relative to this point? Well, because remember, the torque is always R cross F, and we are calculating. Torque depends on your reference point, because R depends on your reference point. If you change your reference point, torque might be different. Torque with respect to this point of the normal force is just 0, because the position of this point, the point where the normal force is acting, is 0 relative to my point. So R is 0, so torque is 0. The same holds for the friction force. The friction force is acting at this point, but that point is R is equal to 0. So both the normal force and the friction force, none of them create a torque. The only force that creates a torque around this point is the weight. And what is the torque created by the weight? What is its magnitude? This is the total torque. It is the torque created by the weight. Well, let's see, this is R. Remember, weight, we had already seen that it acts, the torque the weight creates is as if it is acting at the center of mass. Well, the center of mass is at the center of this ring. So the torque will be the product of the magnitudes. So it is the radius times weight. The magnitude of the weight is mg. The angle between the two. Now let's see, this angle over here is theta. Let's do a bit of geometry. If that angle over there is theta, then this angle over here is also theta. This angle also is theta. No? This is theta. This is 90 minus theta. This is okay. This one over here is theta. This one is theta. So the magnitude of the torque, this is the radius vector. Okay, this is the radius vector, this is the weight vector. The angle between the two is 180 minus theta sine pi minus theta. What is the direction of the torque? This is R, this is W. R cross W, just rotate it. It is into the screen. Into the screen is in the minus z direction. So this is equal to mgr sine theta in the minus z direction. This is the torque. Now, what about the angular acceleration? is the torque divided by the moment of inertia. This is equal to mgr sine theta in the minus z. Well, assuming it's a wheel, the moment of inertia is mr squared. No. I will just keep it to be I. It's not mr squared. We calculated the moment of inertia of a wheel for rotations around its center, and that was mr squared. This is not rotating around its center. So alpha is equal to mgr sine theta over I in the minus z. Now, since now my wheel is rotating around this point, I will tell you that the moment of inertia is 2mr squared. This is the moment of inertia. Now, why it is 2mr squared, we will study on Thursday. So this is equal to g over r sine theta, g over 2r sine theta in the minus z. So the acceleration of the center of mass, the tangential acceleration is just alpha times the distance, that is alpha times r, that is g over 2, g sine theta over 2. Okay, so this is the acceleration of the center of mass. The wheel is accelerating downward with g sine theta over 2. Now, if you remember the example there where we saw in the absence of friction, if you just leave an object on a frictionless surface, it slides down, the acceleration was g times sine theta. Now, in this case, there has to be a friction force to slow it down. And also, since it is slowing it down, now we have justified that the friction force is trying to slow it down. So it's in this direction. The direction is correct. There's still the question, what is the magnitude of the friction force? It's rolling without slipping. There's no relative motion between the surfaces. So it's a static friction. We know its maximum value in terms of the coefficient of static friction, but that doesn't tell us what the magnitude is. Now, in this example, we can determine what the magnitude is. We will be doing it on Thursday. Now, any questions on this one? Now, again, although it's just translational motion, we just converted it into a motion with a fixed rotation axis. And once the rotation axis is fixed, well, everything we had done until now we can use. We calculated the torque. The torque depended only on the weight of the object. From the torque, we could calculate the angular acceleration. And from the angular acceleration, we could determine the acceleration of any point on my rigid body. In particular, the center of mass is accelerating. The tangential acceleration of the center of mass is nothing but g over 2 sine theta.
When the wheel is rolling on the ground, there is no friction force.
True.
Then, ignoring the drag force, it will never stop. You can say that.
Well, practically, yes. But in reality, of course, there is a drag force. Of course, there will be the stick. I mean, the rubber will, although very slightly, it will stick to the ground. It will try to slow it down. But compared to, I mean, if you just compare these two motions, I just push it with a given velocity. This is the distance it covers. If I just roll this, it will go until it hits something. No, it's not slipping, but it is sticking. The rubber will stick to the ground, stick. Furthermore, the ground is not so rigid. It will be very slightly deformed, which will create some backward force in the backward direction, etc. So eventually it will stop, but it will cover a very huge distance compared to that motion. So all these kind of slowing down, the forces that will cause this to slow down, it is negligible compared to all the other forces. Okay, so see you on Thursday.